Thank you, Juan. So my first two lectures, the first lecture this morning will be an introduction to information theory, and then in the afternoon we'll go in more detail involving quantum field theory. And then my last two lectures, Tuesday and Wednesday, are going to be on aspects of general relativity. All of the lectures are meant to be introductory for the school. And hopefully they'll be useful for the other lecturers and also the students, but we'll see. So we'll start with a very short introduction to classical information theory, which is also called Shannon theory. So imagine receiving a message consisting of a string of symbols A or B, a sequence that's random, except that you know that A occurs with probability P and B with probability 1 minus P. When I say random, what I really mean is you know nothing else about what the sequence is going to be. How many bits of information can you extract from a long message of this kind, say with n letters? Well, if there are 2 to the s possible messages, you can extract s bits of information. So we just have to count the messages. For large n, there are going to be p times n occurrences of A and 1 minus p n occurrences of B. So the number of ways to pick pn objects out of n is this. And for large n, it's approximately 2 to the n times s, where s is called the Shannon entropy and is given by this formula. So one way to look at it is if you had agreed with a friend in advance that information was going to be sent through these crazy messages of A's and B's, and if you had arranged a code book, then a friend wishing to convey s bits of information would have picked one out of the possible messages and encoded it in that way. So the exponent is 2 because in information theory, people use logarithms and exponents in base 2. So the total number of messages of length n is roughly 2 to the n times s, and so that's the number of bits of information that you can gain when you observe such a message. It's an asymptotic formula for large S because we use Stirling's formula, only the leading term in it, to estimate the number of possible messages, and we ignored fluctuations in the frequencies. Now suppose more generally that there are k possible symbols, A1 up to AK, and the probability of the ith symbol is p sub I. Well, then you proceed in the same way. And this is the number of possible messages of that kind, assuming that each symbol occurs the expected number of times for large n. And approximating it for large n by Stirling's formula, the number of possible messages is roughly 2 to the n times s, where s is the Shannon entropy of this probability distribution. And it's given by that formula minus the sum of p log p. So that's the general definition of Shannon entropy for any probability distribution. And the number of bits of information you can extract from such a message is always n times the entropy. In other words, it's the logarithm of the number of possible messages. Now, since 2 to the n times s is the number of possible messages, and the number of messages is at least 1, clearly the entropy is always non-negative. To make the entropy 0, there should be only one possible message, which means that one of the letters has probability 1 and the others have probability 0. On the other hand, the maximum possible entropy occurs if the probabilities are all equal and is given by log k, where k is the number of letters in the alphabet. As an exercise, you can prove this using the method of Lagrange multipliers. So it seems a little funny at first that in a subject called information theory, one discusses random messages. So I just wanted to make a remark about that. In some applications, n times s is the number of bits to which you can compress a message. In such applications, the message isn't random, but consists of information that you wish to convey. But in what's called lossless encoding, the encoding program doesn't understand the message and treats it as random. So, for example, a lot of companies that have small websites, customers can get impatient if a website doesn't load quickly. And to load quickly, it has to download some information from the company's server or whatever. And the ability to do that involves conveying rapidly a message that the encoder isn't sophisticated enough to understand. So this lossless encoding is important for a lot of small companies that will lose out if you get impatient with their website. So you can easily imagine a situation in which you could make a better model by not treating the letters as random. For instance, if the letters are words in a message in the English language, then English grammar and syntax would dictate short-range correlations, at least. There might be long-range correlations, but there certainly would be short-range correlations. So a better model would be to incorporate short-range correlations in a classical spin chain with short-range interactions. And then its entropy would be the number of possible long messages in English, or at least a better estimate than if you treat the words as being random. And as I've stressed, even in the ideal gas limit model where we treat each letter as being random, we're making statements that are only natural for large n. So this was a kind of ideal gas model of information theory. If you want to make the analogy with the usual ideal gas more precise, you could introduce a Hamiltonian whose value for the ith symbol is minus log p, so that the probability of the ith symbol in the thermodynamic ensemble is 2 to the minus the Hamiltonian, which is pi. And then, you see, in ignoring the fluctuations in the number of letters, we've ignored the difference between the canonical and microcanonical ensemble. One is defined by probabilities and one by precise frequencies of letters. So this is a standard thing in statistical mechanics, that the ensembles are equivalent for large n. And that equivalence is important in both classical and quantum information theory. Now let's consider a more sophisticated situation where Alice is sending a message to Bob through a noisy channel. So she sends a message that consists of many letters. Each is a random variable x whose possible values are x1 up to xk. But what Bob receives is many copies of a random variable y, drawn from an alphabet with letters y1 up to yr. Bob might confuse some of Alice's letters and misunderstand others. So there's some kind of mapping from what Alice sends to what Bob hears. How many bits of information does Bob gain after Alice has transmitted a message with n letters? Well, we need to introduce a joint probability distribution, p of x and y. It's the probability that Alice sends xi and Bob hears yj. Well, the probability that Bob hears yj, irrespective of what Alice intended, is gotten by summing the joint distribution over whatever Alice might have sent. And if Bob does hear yj, then he tries to estimate what Alice sent. And his estimate is what's called the conditional probability. So the probability of xi given yj, which is usually written by the symbol with the vertical bar, well, it's the joint probability divided by the probability of hearing yj. So the probability of both xi and yj divided by the probability of yj alone is the same thing as the probability of xi if you already know that yj is true. So this is the probability distribution by which Bob would analyze Alice's signal once he's heard whatever he heard. So from Bob's point of view, once he's heard yj, his estimate of the remaining entropy in Alice's signal is just the Shannon entropy of the probability distribution that he would use, which is the conditional probability distribution. So once you've heard yj, the entropy in the signal x is given by the same formula minus p log p as before, but you have to use your new probabilities, which are now the conditional probabilities. So this is the entropy that Bob would attribute to Alice's signal once he's heard whatever he's going to hear. And the average entropy that remains in Alice's signal once Bob has heard y is simply obtained by averaging the residual entropy over what Bob might have heard. So if you sum over all probabilities of what Bob heard times the probability that he heard it times the remaining entropy, where the remaining entropy is given by this, you get what I've written here, where I substituted the definition of the conditional probability, which is this expression here. And a little arithmetic lets you simplify this sum, and you discover that it's equal to the difference of two ordinary entropies, namely the entropy of the joint probability distribution P of xy and the entropy of Bob's distribution P of y. The way that happens is you write the logarithm of the ratio as the difference of two logarithms, this one and this one. Also, you cancel P of y. And here you simply see S of xy, the entropy of the joint probability distribution. Here, x only appears in one place, and if you sum over x, you get Bob's probability P of y, and then you see you have minus S sub y. So from Bob's point of view, the entropy that remains in Alice's signal, once he's heard whatever he's going to hear, is the entropy of the joint distribution minus the entropy of Bob's observed distribution. So as I said, S of xy is the entropy of the joint distribution, and S of y is the entropy of the probability distribution for Bob's observable, which is gotten by summing over I, where here the sum over I, in this term, will produce P of y. So the difference that we just arrived at, Sxy minus Sy, is called the conditional entropy, S of x slash y, where the single vertical bar stands for conditional, as in conditional probabilities. It's the entropy that remains in the probability distribution x once y is known. Well, it was obtained as a sum of conditional entropies, which were positive with positive coefficients, so it's clearly positive. After all, it measures what Bob still doesn't know after hearing whatever he's going to hear, so it ought to be positive. This isn't true quantum mechanically, though, by the way. Now, since Sx was the original information content in Alice's message, and Sxy minus Sy is what Bob didn't learn by observing y, it follows that the information that Bob does gain when he hears y is the difference, which is, well, Sx minus this is Sx minus Sxy plus Sy, and that's called the mutual information. It's the mutual information between x and y. So in the way I presented it, it's what Bob learns about Alice's signal after he hears y. But since the formula turned out to be symmetrical, it also measures what Alice knows about what Bob heard. So it measures what we know about x by observing y, or vice versa. Well, this interpretation convinces us that I of xy must be non-negative. And you can easily prove it directly, but instead we'll deduce it from the properties of one more quantity, which is going to complete our cast of characters in classical information theory. And I'll motivate it as follows. Suppose we're observing a random variable x, for example, the final state in the decays of a radioactive nucleus. We have a theory that predicts a probability distribution for the final state. For example, the prediction might be that the probability of final state I is Q sub I. However, our theory might be wrong, and maybe the decay is actually described by a different probability distribution P with a probability Pi for the ith final state. Well, after observing the decays of n atoms, how sure could we be that the initial hypothesis is wrong? Well, if the correct probability distribution is P, then when we observe n decays, we'll see the ith outcome approximately Pi times n times. And we'll judge the probability of what we've seen to be the following. Well, Qi to the Pin is the probability, if the hypothesis Q is correct, then Qi to the Pin is the probability to see a particular sequence where the ith final state occurs Pin times. We just include a factor Qi each time we observe an outcome whose probability is Qi. And this is the number of sequences with those frequencies. And now we already calculated this number for large n, and it was 2 to the n times the Shannon entropy. So including this other factor, we see that the probability of what we've seen, assuming the initial hypothesis was correct, is given by 2 to the minus n times this sum of logarithms. And that sum is called the relative entropy. Well, it's n times the relative entropy, also called by information theorists the divergence, and it's given by this formula. So that's called the relative entropy between two probability distributions P and Q. And it measures the ability to determine that if you have a hypothesis Q but the correct answer is P, it measures the ability to prove the initial hypothesis is wrong after n trials. So the answer to the question, when will we be sure we were wrong? We'll be sure we're wrong once n times the relative entropy becomes large. And its smallness will determine the confidence about being wrong. So from the derivation, S of P relative to Q is clearly non-negative, and it's 0 only if P equals Q, namely if the initial hypothesis was correct. If the initial hypothesis is wrong, we'll be sure of it once n times the relative entropy is large. Well, this statement ignores noise. If you wanted to include noise, you should, well, the starting point at least, would be what we discussed with conditional entropy, where we discussed a signal from Alice that was observed by Bob modulo some noise. So you should combine the two to make a more precise estimate here, including noise. But we won't go in that direction. So the relative entropy is an important measure of how two probability distributions are different, but it's asymmetric between them. What breaks the symmetry is that we assumed that Q was the initial hypothesis and P was the correct answer. Now we're going to use positivity of relative entropy to prove that the mutual information is positive. So we consider a pair of random variables x and y, and we'll consider two different probability distributions. One, which we call P, is given by a joint probability distribution in which the two may be correlated. So it's given by some distribution P of x and y. All we assume in general is that the P's are non-negative and they add up to 1. Then we could define separate probability distributions if you observe only x or y. So P of x is gotten by summing the joint distribution over y. P of y is gotten by summing the joint distribution over x. So we actually already made this operation once before when we discussed conditional entropy. So this is an important operation of integrating out some variables to get a probability distribution for observations of a smaller number of variables. Now we can define a second probability distribution for x and y by ignoring the correlations between them. If we just take P of x times P of y, that is a probability distribution for x and y. It's one where they are uncorrelated, where the probability to observe one value of x is independent of what value of y is observed. Now we can calculate the joint relative entropy between P, which was some arbitrary distribution, and Q, which is this factorized distribution. So by definition, the relative entropy would be the sum over all pairs of P of x and y times the difference of two logarithms. But in this case, the argument of the second logarithm is a product, so we can write it as a sum of 3 logarithms. And that sum is just a sum of 3 entropies. To turn it into a sum of 3 entropies, you make a manipulation we actually made a moment ago. For example, for this term, since there's no y in here, the only y appears here, and the sum over y will turn P of xy into P of x. And then that will contribute sx. This will contribute sy, and this will be minus sxy. So we found that the mutual information is a special case of a relative entropy. And since relative entropy is positive in general, it follows that mutual information is positive. And moreover, we learn that mutual information is 0 only if the two distributions are the same, meaning that x and y are uncorrelated to begin with. In other words, if y, which Bob observes, is uncorrelated with x, which Alice sent, then he will learn nothing about Alice's signal by observing whatever he observes. That's the case in which the mutual information is 0. So from the formula for mutual information, its positivity is this statement about the entropy, which is also called subadditivity of entropy. Now, the relative entropy has one more very important property, and that'll more or less conclude our introduction to classical information theory. Let x and y be two random variables. And let p sub xy and q sub xy be two probability distributions for the pair. So now we have two functions, p of xy and q of xy. Well, we start with a hypothesis q of xy for the joint probability. But again, if p of xy is the correct answer, after many trials in which we observe x and y, our confidence in being wrong is determined by the relative entropy between them. But suppose we only observe x and not y. Well, then we could describe what we observe by reduced probability distributions px and qx, where you integrate out y from the full distributions. So if we had a hypothesis qxy for the joint distribution, we'd have a hypothesis qx for observing x only. If we observe x only after many trials, the confidence that the hypothesis was wrong is controlled by the relative entropy between px and qx. But it's harder to disprove the initial hypothesis if we observe only x. So the relative entropy between pxy and qxy must be only bigger than that between px and qx. That fact is called monotonicity of relative entropy. It's monotonic under an operation of integrating out some of the variables. It actually has a more general monotonicity that I won't describe. Concretely, suppose we observe a sequence of x's. To estimate how unlikely it was, we'd imagine a sequence of y's to minimize the unlikelihood of the joint sequence. But an actual sequence of y's that we might observe would be only more unlikely than this. So observing y as well as x could only increase our estimate of how unlikely the outcome was given the sequence of the x's. So the relative entropy can only go down upon integrating out some variables and not observing them. Now, I think if you understand what I've said, you should regard it as a proof, but I'll also give a proof in formulas. In formulas, the statement that this relative entropy is bigger than this one amounts to this assertion. And a simple rewrite is given here, where, for example, p of x was added in the numerator and denominator, and the logarithms were combined into one big logarithm. And the left-hand side is a sum of positive terms, because it's the sum with weights p of x of a conditional entropy, conditional relative entropy, of the entropy between conditional probability distributions, p of y given x and q of y given x, that are conditional on observing x. So you might need to think this through later, more carefully looking at the slides, but if you define the conditional probabilities for y that you would use once x is observed, then what we're trying to prove is positive is a sum with positive coefficients of a conditional entropy between two conditional probability distributions for y given x. So that establishes monotonicity of relative entropy. An important special case of monotonicity of relative entropy is called strong subadditivity of entropy. For this, you consider 3 random variables, x, y, and z. So the combined system has a joint probability distribution, p of x, y, z, described by a function of all 3 variables. Alternatively, you could forget the correlations of x with y, z. So you could define a partially factorized probability distribution that's a function of x times a function of y, z, where each of the reduced distributions is gotten by integrating over unobserved variables. So the probability for x only is gotten by summing over y and z, and the probability for y and z is gotten by summing over x. So this is another probability distribution for the combined system where we ignore correlations of x with y, z. So the relative entropy between them is the entropy between x, y, z and p of x, y, z and q, x, y, z. But what if you don't observe z at all? In that case, we should integrate out z everywhere. So we replace p of x, y, z and q of x, y, z by pxy and qxy, which are obtained by summing over z. So we sum pxy z over z to get a probability distribution that's correlated between x and y. But the other one, when we sum over z, turns out to be uncorrelated. That's because in Q, we already ignored correlations of x with yz. And if we throw away z, we will be ignoring correlations of x with y. Now we'd have a relative entropy between these two. So monotonicity of relative entropy tells us that one of these is at least as big as the other. But we observed a moment ago that in this kind of situation, relative entropy reduces to mutual information. So the relative entropy between our starting distributions is the mutual information between x and yz, which is given by this sum of 3 entropies. And the relative entropy between these two is another mutual information, so it's the sum of these 3 entropies. So the monotonicity statement becomes this, or after a small rearrangement, we get this inequality among 4 entropies, which is called strong subadditivity.
I think that's supposed to be a y, sy.
Thank you. You're correct. Yeah, sorry. This is sy here. Thank you. This, I guess this version is correct. So remarkably, the same statement is true in quantum mechanics, where it's both powerful and surprising. So I will make one more comment before we get to the quantum mechanical case. We repeatedly use the ability to define a conditional probability distribution, conditional on observing something. For example, if Bob heard Y, he updates his estimate of Alice's probabilities, and so on. This doesn't have a good analog in quantum mechanics, and it's a bit of a miracle that many statements have quantum mechanical analogs. But the most miraculous is certainly strong subadditivity. And the interesting statements in quantum information theory usually are either more elementary or else they're proved using strong subadditivity. So, okay, we're finished with the first part of the lecture, which was on classical information theory. Maybe we could just take a couple moments for a question, if there's one. Okay, if not, we'll turn on to quantum information theory. So quantum mechanics is always dealing with probabilities, but the real quantum analog of a classical probability distribution isn't a quantum state, but rather a density matrix. So depending on your view of quantum mechanics, you might believe that there's a pure quantum mechanical state for the whole universe that depends on all possible degrees of freedom. But even if that's the case, you ordinarily study a subsystem that can't be described by itself by a pure state. So for an idealized case, let A be a subsystem of interest with a Hilbert space H sub A, and let B be everything else, or maybe all the rest of the universe, with a Hilbert space H sub B. So the combined system has a tensor product Hilbert space HAB, the tensor product of HA and HB. Well, things are simple if a state vector of the combined system is the tensor product of a state vector in HA and one in HB. In that case, one can assume that they all are unit vectors without any essential loss. And in this situation, measurements of the A system can be carried out by forgetting about the B system and using the state vector psi sub A. So if O sub A is any operator on H sub A, the corresponding operator on H sub AB is OA tensor of the identity on B. Its expectation value in a factorized state is the product of expectation values. And since the identity operator has a unit expectation value, that reduces to an expectation value in the state psi sub A. So in the case of a factorized state, we could forget about the B system and just describe the A system by a pure state psi sub A. But a generic pure state of the combined system is not a product state. Instead, it's entangled. So if HA and HB have dimensions n and m, a generic state could be represented as an n by m matrix. For instance, in the 2 by 3 case, a generic state of the combined system would be something like that with 6 matrix elements. By unitary transformations on HA on an HB, you can transform the combined state using n by n and m by m unitaries. And the canonical form under that operation is a diagonal matrix with positive numbers on the diagonal and some extra rows or columns of zeros. For example, in the 2 by 3 case, such a matrix could be put in this form by a joint unitary transformation. Now, without actually making the unitary transformation, a slightly more invariant way to say it is that any pure state can be written in this form, where we can assume that psi A and psi B are orthonormal, and that the p's are positive. If one of the p's were 0, we would drop it from the sum. That's called the Schmidt decomposition of a state of a so-called bipartite system. In general, we shouldn't assume that the psi A's and psi B's are bases, because there may not be enough of them, but they are orthonormal vectors. The condition for psi AB to be a unit vector is that the sum of the p's is 1, so we could think of the p's as probabilities. If you're planning to observe only the A system, you would describe the situation by saying that with probability p, the unobserved system is in the state psi IB, and your system is in the state psi IA. What's the expectation value in such a state of an operator OA that only acts on A? Well, we have to take the matrix element in the state of OA tensored with the identity. It's the same computation as before, except that there's more than one term in the sum. Before, we just had, before the state was a simple tensor product, but now it's a sum of simple tensor products. And since the psi bi are orthogonal, the different terms in the sum don't interfere when we act with the identity operator on the B state. So the matrix element of an operator that only acts on A is given by a sum of what we had before with probabilities pi. So it's given by this formula. And that's the same as the trace in the Hilbert space of the operator OA times what's called the density matrix rho sub A. Rho sub A is a matrix given by that formula. So if we're only going to make measurements on system A, we do not need a wave function of the universe. It suffices to have a density matrix for system A. Now, from the definition, we see that rho A is Hermitian and positive semi-definite. And that's the only restriction on it. Well, sorry, its trace is 1. I'm not sure if I wrote that. Yeah. So these are the only restrictions on rho sub A, because every Hermitian positive semi-definite matrix of trace 1 can be written like this, where the p's add up to 1. You just need to know that a Hermitian matrix can be diagonalized by a unitary transformation, and then the psi's are the eigenvectors, and the p's are the diagonal matrix elements after the matrix is diagonalized. So, since every Hermitian positive semi-definite matrix of trace 1 is of this form, every such matrix is the density matrix of a bipartite state, meaning a pure state of a system AB. Every density matrix on system A is the density matrix. Sorry. Every matrix with these properties is called a density matrix. And every density matrix of system A can arise in the way we've described from a pure state of a system AB. That's pretty much a restatement of what we've already said. Given a matrix that's Hermitian, positive, semi-definite, and has trace 1, we diagonalize it, which means we put it in this form. And once we put it in that form, we can undo what we did before. Given this formula, we introduce a second Hilbert space with orthonormal states psi bi, and we write down this formula for psi ab. And as we've said already, that psi ab will give rise to the density matrix on the previous slide. So not only does every density matrix arise from every density matrix arises from such a bipartite state, and conversely, every bipartite state produces a density matrix. Now, if we're given rho, then this is an example of a bipartite state that would lead to rho as the density matrix on system A. But it's not unique because the psi b's were orthonormal vectors in HB, but that didn't determine them uniquely. However, it determines them up to a unitary transformation of system B. So psi AB, after we choose B, is unique up to a unitary transformation of H sub B. That's an important fact to bear in mind later. Psi AB is called the purification of a density matrix rho A by converting it to realizing it as the density matrix from some pure state. The pure state isn't unique, but it's unique up to a unitary transformation of the second system. So as I said, psi AB is called a purification of the density matrix of system A. The existence of purifications is a nice property of quantum mechanics with no classical analog. The classical analog of a density matrix is a probability distribution, and there's no such thing as purifying a probability distribution. You can't add more variables. A pure probability distribution would be one where one outcome has probability 1 and the rest are 0. But once a probability distribution has become impure, there's no way to make it pure by adding more variables. If there's more than one term in the Schmidt decomposition, we say that the systems A and B are entangled. If there's only one term, we have an unentangled tensor product state. And as I said at the beginning, that means that system A can be described by a pure state, or equivalently, the density matrix has rank 1. If the density matrix has rank higher than 1, we say that system A is in a mixed state. If the density matrix is invertible, we say that A is fully mixed. That's the situation in quantum field theory. And if it's a multiple of the identity, we say that A is maximally mixed. In the general case, whatever the density matrix is, you'll describe all measurements of system A correctly if you say that the system is in the state psi I S of A with probability P sub I. But you have to be cautious about that interpretation because in general this decomposition isn't unique. It's unique if you want the number of terms to be as small as possible or if you want the psi AIs to be orthonormal. But more generally it's not unique. So if Alice prepares a quantum system to be in the pure state psi I with probability pi, then even if she provides you with many identical copies of whatever she's prepared, there's no way to determine the psi I and the pi. A measurement will only depend on rho, and rho does not uniquely determine the psi I and the pi. Beyond measuring rho, there's no way to get information about how the system was prepared.
You're talking about multiple identical copies?
Alice provides you with multiple identical copies of a system in the same density matrix. You can measure the density matrix, but you can learn nothing else about how she prepared the system. Any other questions? Yes?
Are there any actually guidelines in choosing the system B that will provide certification?
Well, the question is, what is the system B? In a real experiment, a B will probably present itself. If you're making mathematical arguments, there may or may not be a natural B. Sometimes you make an argument that, we'll give examples in a moment, where you simply use the fact that abstractly purifications exist, and then there's no natural B. In a real life problem, there might be a natural B. Any other questions or comments?
What is a generic operator that just acts on the two systems? Let's say for some reason there's a particular A and B that's important because
Yes.
I care about this particular set of
Yes.
operators for A and then
Yes.
it's my lab.
Yes. For example, let A and B be states of two spin-half particles. So a typical operator that acts on both of them would be the dot product of the two spin operators, S1 dot S2.
And so how will that descend to someone who only has access to the density matrix for A? It'll just be some sort of weird transformation from one row A to another.
Well, if you want to study such an operator, you need a density matrix for the whole system, not just for system A. The density matrix for system A is only useful if you're only going to be discussing observations of system A. Yes?
We assume the dimension of HB is less than or equal to the dimension of HA, right?
We didn't assume that. So everything I've said was valid for every possibility for the dimension of HB. So if B is a naturally occurring system, it will have whatever dimension it does. When you're making a mathematical argument, you'll pick a B to be big enough to make your argument, usually.
Well, for purifications, you need the dimension of B to be larger than
Yes.
Yeah.
For purification, as Juan says, B has a dimension at least as large as A. Yeah. Assuming the density matrix was invertible. Any other questions? Now, maybe before I go on, I should just remind you why it's impractical to not use density matrices. So consider an atom that's illuminated by photons. And you're observing the atom. The photons pass through the cavity. They're either scattered or not scattered. You don't observe the photons afterwards. You keep observing the atoms. So after a certain time, the atom will be alone. For example, it might emit a photon and later, it might absorb a photon and later re-emit it and go down to the ground state. But the atom always ends up alone in the cavity. After the atom has interacted with n photons, for a pure state description, you'd need a joint wave function for the atom, all n photons, and whatever else the photons have interacted with. So the mathematical machinery would get bigger and bigger, even though, assuming you only observe the atom, the physical situation isn't changing. The density matrix gives you a mathematical framework for studying this that doesn't change regardless of what's happened in the past. All you need is a density matrix for the atom. So atomic physicists who are studying a situation like this would certainly describe it by density matrix for the atom, not a pure state for everything that the atom could have interacted with. Okay, that completes our basic definition of a density matrix. Now we'll do something with them, which is to define the von Neumann entropy. So the von Neumann entropy of a density matrix is defined by a formula analogous to the Shannon entropy of a probability distribution. So instead of minus the sum of p log p, it's minus the trace of rho log rho. But if rho is diagonalized, then minus the trace of rho log rho turns into minus the sum of p log p. The same as the Shannon entropy of a classical probability distribution with the p's as probabilities. So an immediate consequence is that just as for the Shannon entropy, the von Neumann entropy is non-negative, with equality only if one of the p's is 1 and the other is 0, which corresponds to a pure state. Also, the formula that S is minus the sum of p log p implies the same upper bound on the entropy that we had classically for a system with k states. The entropy is no bigger than log k. With equality only if the probabilities are equal, which here means that rho is a multiple of the identity. If that's the case, as I said before, we say that A is in a maximally mixed state. In fact, the von Neumann entropy is in many ways analogous to the Shannon entropy as seen in these properties. But the explanations are usually more subtle and there are key differences. Well, here's a nice property of the von Neumann entropy that does not have a classical analog. Suppose that a bipartite system AB is in a pure state with this Schmidt decomposition. Then the density matrices of systems A and B are given by these formulas, where we wrote down rho sub A before and rho B is deduced in the same way. The same constants pi appear in each, so clearly the two entropies are equal. So a system A and a purifying system B always have the same entropy. That can't really have a classical analog because there's no such thing as a purifying system. Now, an important property of the von Neumann entropy is its concavity. So to explain this, let rho 1 and rho 2 be two density matrices. And define a new density matrix, which is a linear combination of rho 1 and rho 2 with positive coefficients. So rho of t is t times rho 1 plus 1 minus t times rho 2. Then I claim that so first of all, rho of t is a density matrix for all t, because since we use positive coefficients, it's a positive semi-definite matrix, and because the coefficients add to 1, its trace is 1. Also, it's Hermitian because it's a sum of Hermitian matrices. I claim that the second derivative of its entropy is non-positive. Well, to show this, you first compute the first derivative of the entropy. And remembering that the entropy was the trace of minus rho log rho, you find out that this is the first derivative of the entropy. It's not a completely trivial statement. It'll be trivial to prove if you assume that rho of t is always diagonal, but it's true even if rho of t isn't always diagonal. I'm leaving it as an exercise, but I should have remarked at the beginning that there's a written version of this lecture on the archive, and if you have trouble with the exercise, you could peek, because it's explained in a footnote there. Now, okay, so we want to use this formula, and we will use a candy formula for log rho that we'll use a couple times also tomorrow. So log rho is given by this integral. And to prove that, you see, rho being a Hermitian matrix could be diagonalized. And then this is true if it's true for each eigenvalue. So it just reduces to a statement about integrals of real functions. the fact that we're integrating a matrix-valued function isn't important. Now, another fact is that rho of t was defined to be linear in t. And that means that the second derivative of rho is 0. So when you calculate the second derivative of s, you don't have to differentiate rho dot, but you do have to differentiate log rho. But if you use this formula for log rho, then it's convenient to differentiate log rho, and you get this nice formula down here. The integrand is positive because it's the trace of b squared where b is a self-adjoint operator, namely this one. So the second derivative of the entropy is minus the integral of something positive, so it's negative. And if you're a little more careful, you'll see it's strictly negative, except under very strong conditions. So in other words, this function s of rho of t is concave. So a function whose second derivative is negative bends down. And it has the property, I don't know if this is visible or not, but a function whose second derivative is negative always lies above the graph, sorry, the straight line connecting any 2 points on its graph. So that gives us an inequality that the average of 2 values, a point on the graph is given by the average of the values at the endpoints, and it's less than the value at the average. So concavity gives this inequality that a linear combination of entropies is less than the entropy of the average density matrix. And more generally, you could consider any number of density matrices and any non-negative numbers adding up to 1, and a concave function has the property that the average of some of its values is less than the value at the average point. So that generalizes this fact. And once you know it, well, you might know it as a fact about concave functions, but also as an exercise, you could try to prove it by induction starting from this. That more generally, if you have any number of density matrices, the sum of pi times their entropies is less than the entropy of the average density matrix. So that might be described by saying that entropy can only increase under mixing of states, where here state means density matrix. So one extreme case would be that the rows could be pure states. Sorry, rank 1 density matrices of pure states. Then their entropies are 0. But S of rho is a mixed state. Sorry, rho is a mixed state. The row I could have rank 1. Then their density matrices have 0 entropy. Then they have 0 entropy. But rho is a mixed state, so its entropy is positive. So that's what this inequality means in that case. So the difference of S of rho minus the linear combination is called the Halevo information, or Halevo chi. And it often appears in different situations. Here's an example. Let rho be any density matrix, and in some basis, let rho d be the corresponding diagonal density matrix. If rho is a density matrix, which means just a positive semi-definite Hermitian matrix, that means its diagonal matrix elements are all positive semi-definite. And if you throw away the off-diagonal matrix elements, you'll get a new density matrix, rho sub d. Then let's try to apply our logic to a linear combination of rho sub d and rho. So we define this rho of t. In this case, the first derivative of the entropy is 0 at t equals 0. You might need to think through the statement more carefully later. And by concavity, the second derivative is negative. So it follows that the entropy at 1 is less than the entropy at 0, or that S of rho is equal to or less than S of rho d. So that's a special case of the inequality for entropy under mixing. I'm sorry that this explanation may have been hard to follow. I wrote it down because we'll wanted in a moment for positivity of relative entropy. Any questions? Yes?
Well, this is a comment, but you can get the same result directly as an averaging statement by averaging over phases that you multiply the off-diagonal elements by. It's just another proof of the same statement.
Thank you. Any other questions, comments, or questions? Well, just as for classical probability distributions for density matrices, you can always integrate out an unobserved system and get a reduced density matrix for a subsystem. So classically, if we had a joint probability distribution, we integrated out y to get a probability distribution for x only. The quantum analog of that, sorry, what you meant was to prove it from the entropy inequality for mixing.
Yeah.
Perhaps, I see, yes.
Yeah.
Right, yeah. So what Matt is saying is actually quite simple, and I wish I'd thought of it in preparing these slides. So what he said is that if you conjugate rho by a diagonal matrix, diagonal unitary matrix, you'll get a new density matrix. And if you pick a lot of those diagonal unitary matrices, rho d is an average of a bunch of density matrices. The individual density matrices all have the same entropy. And the entropy inequality for mixing, this one, will give what I proved here, but in a less technical sounding way, perhaps. So that's a nice proof. Thank you. I might crack the written version of this. So classically, given a joint probability distribution, we integrated over one variable to get a probability distribution for x only. The quantum analog is a partial trace. Suppose AB is a bipartite system with Hilbert space HA tensor HB and density matrix rho AB. Now, concretely, if we have an orthonormal basis for HA that I'll call A sub I, and if B sub alpha is an orthonormal basis for H sub B, a density matrix for the combined system takes this general form. But if you're going to measure system A only, you can get a reduced density matrix by setting alpha equals alpha prime and summing. So if you set alpha equals alpha prime and sum, you get a density matrix for A only. That's usually written as a partial trace. Rho A is the trace over HB of rho AB. The idea being that we took a trace over the matrix elements that act on system B. This was alpha and alpha prime, leaving a density matrix for HA. Likewise, summing over I to eliminate HA, we would get rho B, which is the trace over HA of rho AB. So the partial trace is a very important operation, which is the analog in classical probability theory of summing over one variable to get a reduced probability distribution for remaining variables. It's now possible to formally imitate some of the other definitions that we made in the classical case. For example, if AB is a bipartite system, we define what's called quantum conditional entropy by the same formula as before, SAB minus SB, and we write it by the same notation, or similar notation, SA/B. But I have to warn you that the name is deceptive because there isn't a quantum notion of conditional probabilities. So classical conditional entropy was the average value of a conditional probability distribution, and that made its positivity manifest. Quantum conditional entropy isn't entropy conditional in anything. There isn't such a good notion quantum mechanically. And in fact, it's not necessarily positive. It can be negative. For an example, suppose that the system AB is in an entangled pure state. Then SAB is 0, But since the system B is in a mixed state, SB is positive. So SA/B is negative, which certainly shows that it's not a conditional probability distribution. It's not a conditional entropy in the classical sense. Nevertheless, you can give a reasonable physical interpretation to S of AB, which we may or may not have time for in this lecture. We'll see. I might come back to it. We'll see. Another classical definition worth imitating is the mutual information. So given a bipartite system with density matrix AB, rho AB, the mutual information is defined just as it is classically. But here we're more fortunate, and the quantum mutual information is non-negative, just as it is classically. Moreover, it's zero if and only if the density matrix factorizes, in the sense that rho AB is a tensor product of rho A and rho B, which is the analog of having no correlations classically. So just as in the classical case, positivity of mutual information is called subadditivity of entropy. So before proving positivity of mutual information, I'll explain an interesting corollary. Conditional entropy SA/B can be negative, but the possibility of purifying a density matrix gives a lower bound. Let C be such that ABC is in a pure state. Now remember that in general, if XY is in a pure state, then SX equals SY. So if ABC is in a pure state, SAB equals SC, and SB equals SAC. Because C is purifying AB, AC is purifying B, since ABC is in a pure state. So, well, SAB minus SB, I substitute for SAB as SC and for SB as SAC. But positivity of mutual information says that SC minus SAC is equal to or bigger than minus SA. If I moved the minus SA to the left, I'd have the mutual information between A and C, and that's non-negative. So the conditional entropy doesn't have to be positive as it is classically, but it's bigger than minus SA, which is called the Araki-Lieb inequality. It's saturated if SAB is 0, which, as we know, implies that SA equals SB. So what I've explained is a typical argument exploiting the existence of purifications. Now, just as in the classical case, to understand positivity of mutual information, it helps to first define the relative entropy. Suppose that rho and sigma are two density matrices on the same Hilbert space H. Then the relative entropy can be defined by imitating the classical formula. It turns out to have the same interpretation that it does classically. If your hypothesis is that a quantum system is defined by sigma, but it's actually described by rho, then to learn you're wrong, you need to observe n copies, where n times the relative entropy is large. So we'll possibly have time for that, but otherwise I'll refer you to the written version of the talk. Just as classically, it turns out that the relative entropy is always non-negative. So we'll prove that in a moment, but first we'll use it to prove that the mutual information is non-negative. And here the proof is exactly the same as it was classically, or it can be obtained by imitating the classical proof, just replacing density matrices with, probability distributions with density matrices. In the classical proof, remember, we started with a probability distribution, and we compared it to another one in which the two subsystems were uncorrelated. So the analog of that here, given rho AB, we suppressed the correlations by replacing rho AB with rho A tensor rho B, which I'll call sigma AB. So replacing rho AB with rho A tensor rho B does not affect observations only of A or only of B, but it suppresses correlations between A and B. Then we observe that log of sigma AB is given by a simple formula. So the relative entropy between rho AB and sigma AB can be computed rather as we did classically, and it turns out to be the mutual information. So positivity of mutual information is a special case of monotonicity of relative entropy. And just as classically, it's also called subadditivity of entropy. So we showed that positivity of mutual information follows from positivity of relative entropy. But to prove positivity of relative entropy, we're going to use that inequality we discussed a couple moments ago where Matt suggested another proof. First, pick a basis where sigma is diagonal. If rho is, we want to look at S of rho relative to sigma. If rho is diagonal on the same basis as sigma, what we want reduces to the classical case. For if sigma and rho are diagonal matrices, then the relative entropy, everything being diagonal, quantum mechanics reduces basically to classical physics. So we would get a classical relative entropy, and we already know that classical relative entropy is non-negative. Of course, in general, rho is not diagonal on the same basis as sigma. Let rho d be obtained from rho by dropping off diagonal matrix elements in the basis in which sigma is diagonal. Then straight from the definitions, if you just write down the definition of relative entropy and of relative entropy, this relative entropy, and of von Neumann entropies, you'll discover that the relative entropy we want is the relative entropy of two diagonal things plus a correction involving von Neumann entropies. But we just proved an inequality for the von Neumann entropies a little while ago using concavity. And we proved on the last slide that this is positive. So it follows that relative entropy is positive in general. Well, do we dare to hope that relative entropy is monotonic as it is classically? Well, the answer is yes, as first proved by Lieb and Ruskay. And I consider it kind of a miracle, because since there's no such thing as a joint probability distributions, the intuition behind the classical statement is not applicable.
Edward?
Yes?
Would you, in your experience, does the relative entropy do a good job of distinguishing physically dissimilar density matrices?
Well,
Or, sorry, density matrices corresponding to physically dissimilar mixed states?
well, if we have time, but in any case, in the written version, you can read the fact that the best you can do to distinguish hypothesis sigma from an actual answer rho is given by the relative entropy.
Well, I understand that, but there might be, like, it's because of, like, one weird thing as opposed to the thing in general.
Well, I can't guarantee that the relative, if, for example, there's a limitation on what measurements you can actually make, then the relative entropy might not be the best criterion. It's the best.
Don't inject much energy into the system.
Okay.
Okay, sorry.
Okay. You can certainly imagine a situation where the measurements suggested by the relative entropy are impractical. Anyway, what I was trying to say is that strong subadditivity is a miracle because the intuition behind it in the classical case is not applicable. On the contrary, the shoe is on the other foot. Strong subadditivity is ultimately used to prove that quantities we've defined formally do have properties somewhat similar to the classical case. So if you want to know that quantum mutual information deserves its name, you really need strong subadditivity. Well, I'll at least try to give you a hint of that fact. So there are different statements of monotonicity of relative entropy, but a basic one is monotonicity under partial trace. So if AB is a bipartite system with two density matrices rho and sigma, as we keep doing, you can take a partial trace on B to get reduced density matrices on A. And monotonicity of relative entropy says that taking a partial trace can only reduce the relative entropy. So that's part of what was proved by Lieb and Ruskay. And it's analogous to what we did classically, where we showed that integrating out one variable can only reduce the relative entropy. So one of our main goals in lecture 2 will be to describe how to prove this. So we won't discuss that now. But I do want to show that it has strong subadditivity as a corollary. And for this, we imitate the classical discussion. We consider a tripartite system ABC with density matrix rho ABC. And then there are reduced density matrices where we integrate out some variables. And we define a second density matrix where we ignore correlations between A and BC. You might remember that classically we did precisely that. If you further decide to ignore C, you would trace out C and define rho AB this way, but sigma AB would now be a simple tensor product, because sigma ABC is already a tensor product. And now we can look at monotonicity under partial trace in this situation. It says that this relative entropy is bigger than this one. But when we were discussing positivity of mutual information, we explained that in this situation where sigma is obtained from rho by ignoring some correlations, the relative entropy reduces to a mutual information, which is a sum of entropies. And likewise here. So the monotonicity inequality becomes monotonicity of mutual information, or equivalently, it becomes strong subadditivity, which I think I wrote correctly this time. And these steps are exactly the same as they were classically. Using purifications, you can find various equivalent statements. Suppose that ABCD is in a pure state. Well, that means that CD purifies AB and D purifies ABC, because any of the complete tensor products with the ABCD, which is in a pure state. So the inequality, after substituting for SAB and SABC by these, becomes this one. And that says that a certain sum of two conditional entropies is non-negative. So as we discussed earlier, conditional entropy can be negative. This conditional entropy can be negative. But the sum of conditional entropies of C between two other systems, D and B, is non-negative. That's related to what people call monogamy of entanglements. A qubit in C can be entangled with D, which reduces SCD, or it could be entangled with B, reducing SBC, but it can't be entangled with both of them. So you could think of this as a general statement of monogamy of entanglement. As I've said, classically the intuition behind monotonicity of mutual information, or as I didn't quite say, I think, but classically the intuition is that knowing both B and C will tell you at least as much about A as you would learn by knowing B only. Because remember, mutual information classically tells you what you learned about A if you know B, or what you know about A if you know BC. Quantum mechanically, it's just not obvious that the formal definition fits that intuition. It turns out that you can show it does, but you have to use monotonicity of relative entropy or strong subadditivity. In general, strong subadditivity is the key to most of the interesting statements that are not more trivial. Statements that are not more trivial are deduced from strong subadditivity. So, any questions here? Yes?
So you said at one point that conditional probabilities are ill-defined in quantum mechanics. Could you elaborate on that a bit?
Well, classically, you have a joint probability distribution for all observables. Quantum mechanically, you do not. The whole idea of Bell's inequality, for example, the property of quantum mechanics that people sometimes consider, well, at any rate, that's highly counterintuitive for most of us, is that there does not quantum mechanically exist a joint probability distribution for all the observables.
Yeah, but we can define probability distribution in the sense of sequence measurements.
This is fine, but you can't define it without specifying which sequence of measurements you're going to make. So whatever you can do isn't adequate to give a simple interpretation, such as we have classically, for notions such as conditional entropy. After all, classically, conditional entropy is defined without saying what kind of measurements you're planning to make. If you give a detailed explanation of what you're going to do, you might have an intuition about it. But there's obviously can't be such a story quantum mechanically, since conditional entropy can be negative. Any other comments or questions? Yes?
Doesn't that kind of not jive with this? Because shouldn't our intuition be that gaining knowledge about the system is going to change the system? And this seems to ignore that 100%.
I just want to reiterate that classically there's a joint probability distribution for all observables, and we use that in classical information theory. That doesn't have an analog in quantum mechanics, and some of the things that follow from it, like positivity of mutual information, positivity of relative conditional entropy, are untrue. But some consequences that follow from the usual intuition are true. I think it's surprising when they're true, and the central surprise is strong subadditivity. Once we start using density matrices, there are a few more tools we should add to our toolkit. So first, let's discuss measurements. Textbooks begin with projective measurements, where you project onto orthogonal subspaces of a Hilbert space of quantum states. So you pick positive commuting Hermitian projection operators, pi sub s. They add up to 1. Well, this just says that they're projection operators, and this says they commute. So you take, in a classical measurement, or what's called a projective measurement, you have a bunch of commuting projection operators that add up to 1. A measurement involving these projection operators has outcome s with probability p sub s. The probabilities add up to 1 because the projection operators add up to 1. If instead of a pure state, the system is described by a density matrix rho, then this formula is generalized like so. And the probabilities still add up to 1 for the same reason. But Alice can make a more general type of measurement using an auxiliary system C with Hilbert space curly C. We suppose that curly C is s-dimensional with a basis of states S. So she initializes her system in the state 1. She acts on the combined system C tensor H with a unitary transformation U. She achieves this by suitably adjusting a time-dependent Hamiltonian that couples her, that acts on her system, the combined system. She chooses U so that for any psi in H, one tensor psi is mapped to the most general thing it could be mapped to, which is a linear combination of basis vectors of the auxiliary system C times something in H, which is a linear function of psi. It has to be linear because U is a linear transformation. So this is the most general thing that U could possibly do. Unitarity of U implies that the sum of ES dagger ES is 1, but that's the only general constraint on the E's. Then Alice makes a projective measurement of the combined system using the commuting projection operators, where she projects the auxiliary system onto the state S. And she does nothing to the original system. The probability of outcome S is P sub S, given by the same formula as before. Well, given what the state is she's acting on, and given that her projection operator projects onto S, the probability is given by the norm of this part of the state. So this is the probability of outcome S, which we can write this way. And more generally, if the initial system had a density matrix rho, the probability of outcome S is this one. And the P's are non-negative because ES dagger ES is non-negative. And they add up to 1 because the sum of ES dagger ES is 1. But the ES dagger ES are not commuting projection operators. They're just non-negative Hermitian operators that add to 1. What we've described is a more general kind of quantum mechanical measurement of the original system. In the jargon, it's a positive operator valued measurement, or POVM. So this is the most general way you can measure a quantum system. Now let's view this from another point of view. How can a density matrix evolve? The usual Hamiltonian evolution of a state is that psi goes to u psi for a unitary operator u. On the density matrix, it corresponds to conjugation. Rho goes to u rho u inverse. That's what you probably learned in your quantum mechanics textbooks. But let's consider Alice with her extended system, C tensor H. She initializes the extended system with this density matrix, rho for the original system and the projection operator onto state 1 for the auxiliary system. She applies the same unitary u as before, mapping rho hat by conjugation, but in more detail, she maps it to this. Then she throws away the auxiliary system C. She either forgets about it, throws it away, or decides not to look at it anymore. So we take a partial trace and get a density matrix on the original system, and that's gotten by tracing out C, or in other words, by summing over S, and we find that the new density matrix of the original system is the sum of ES rho, ES dagger. So if there had only been one E sub S, that would reduce to the formula that's most often seen in textbooks, because if there's only one ES, it would have to be unitary, and this would reduce to this. But this is a more general formula by which a density matrix can evolve. So we found a more general evolution of density matrices. The operation that takes rho to this, where the sum of ES dagger ES is 1, is called a quantum channel, and the ES are called Krauss operators. And this is actually the most general physically sensible evolution of a density matrix, and a POVM is the most general possible measurement.
But in the POVM, rho doesn't, it just goes to one of those terms on the...
No, rho is mapped to this sum.
Even if she knows what...
Oh no, if she makes a measurement, then it would be mapped to one of these. But if she applies these operations and then throws away the auxiliary system and doesn't observe it anymore, you would describe the system like so. If she measures S, we would not take a partial trace over the auxiliary system. We would just project onto the part of the state that corresponds to S, and that would be the same thing without the sum over S and dividing by P sub S to normalize it properly. Any other comments or questions? Yes?
What happens if the rho hat is not a part of?
Well, this was analysis control. Rho was anything. Alice brought in an auxiliary system, which she initialized before bringing it in this state. So Alice created a product, and then she carried out the operations I described. And the density matrix she creates at the end is this one. And so this is a physically sensible evolution. It's not unitary because it involved taking a partial trace or forgetting a subsystem. But it's a physically sensible evolution from here to here. And it's called a quantum channel. It's actually, modulo a couple technicalities, the most general physically sensible evolution of density matrices. Now let rho and sigma be two different density matrices on H. We want to know what happens to the relative entropy between them when we apply a quantum channel mapping rho and sigma to these. Well, the first step of initialization, where you replace rho and sigma by their tensor products with this one projection operator on state 1, doesn't change anything. You can check that formally from the definitions if you want to be sure. The second step, conjugating by a unitary matrix U, also doesn't change anything because the definition of relative entropy was manifestly invariant under conjugation. Finally, the last step was a partial trace, which can only reduce the relative entropy. So relative entropy can only go down under a quantum channel. And this is the most general statement of monotonicity of relative entropy. So as an example, suppose sigma is a thermal density matrix at some temperature. So z is the partition function, a normalizing factor so that trace sigma equals 1. So log sigma is minus beta h minus log z. And so you can compute that the relative entropy between any density matrix rho and sigma, well, you can compute it and get a nice formula for it. And the formula involves the expectation value of h in the state, or trace of rho h, which I've called the expectation value of the energy, E of rho. And you'll find that the relative entropy of any density matrix with thermal density matrix is the free energy, as it's usually called, of the density matrix rho, plus a constant log z. But, well, you could compute the constant or remember it from thermodynamics, but the log z term is independent of rho and gives a constant that makes S of sigma with itself 0, which tells you that the relative entropy is a free energy difference between rho and sigma. So I use the fact that S of sigma and sigma is 0 to determine the log z term. But what we determine it to be is something, if you think about it for a bit, you'll remember from having learned statistical mechanics. Now consider any evolution of the system, that is any quantum channel, that preserves thermal equilibrium at inverse temperature beta. So this channel maps sigma to itself, but it maps rho to a generally different density matrix rho prime. The relative entropy can only go down under a quantum channel, so S of rho relative to sigma is only bigger than S of rho prime relative to sigma. And therefore, the free energy of rho can only be bigger than the free energy of rho prime. In other words, under a quantum channel that preserves thermal equilibrium, the free energy can only go down. Equivalently, the relative entropy with a thermal state can only go down under any quantum channel that preserves the thermal state. That's an aspect of the second law of thermodynamics. If you stir a system in a way that maps thermal equilibrium at temperature T to thermal equilibrium at the same temperature, it moves any density matrix closer to thermal equilibrium at temperature T. I wanted to conclude the lecture by giving a couple examples that were aimed to help you understand the statement, well, understand the analogies between the quantum concepts and the classical concepts, and also understand how strong subadditivity is important in establishing those analogies. So since we only have 5 minutes, I won't be able to explain most of that, so I'll refer you to the written version if you want to see more. And I will use the 5 minutes to say a little bit about something which was chosen, possibly not as the simplest example, but as the one that later lecturers were most likely to want as backgrounds. Sorry. I have some exercises on quantum channels, but we'll have to let you look at them later. And there is a longer list of exercises in the written version. So instead, we'll use the last 5 minutes on quantum teleportation. So the elementary example of teleportation is that Alice has in her possession a qubit A0, which is a quantum system with a two-dimensional Hilbert space. She'd like to help Bob create in his lab a qubit in a state identical to A0. But suppose it's too hard to send a qubit, and she wants to communicate by sending a classical message on the telephone. If she knows the state of her qubit, she tells Bob what the state is, and he creates an identical one in his lab. But if Alice does not know the state of her qubit, she's out of luck, because there's no way to find the state of her qubit by a measurement. If she makes a measurement, she'll learn something about what the state was, but she'll destroy the remaining information, and she'll never be able to learn what this original state had been. She can tell Bob what she learns, but what she learns will give only a very partial picture. However, suppose that Alice and Bob have previously shared a qubit pair in a known entangled state, for example, this one. But it's important they know what the state is. Alice might have created it in her lab, and Bob came to visit and brought it home, keeping the quantum state of B1 carefully undisturbed. In this case, Alice can solve the problem. To do this, Alice has now access to her unknown state A0, and also to a state A1, which is in this state together with Bob. To solve the problem, she makes a joint measurement of the system A0, A1 in a basis chosen so that no matter what the answer is, she learns nothing about the prior state of A0. But if she learns nothing, she also forgets nothing. She loses no information about A0. But after getting her measurement, she knows the full state of the system, and she can tell Bob how to create A0. To see how this works, I'll describe a specific measurement Alice can make that will shed no light on the state of A0. She projects the combined system A0 and A1 on the basis of 4 states I've written. The 4 states are chosen so that the reduced density matrix of A0 is always maximally mixed, a multiple of the identity, no matter which of these 4 states you picked. That's because the probability for A0 to be 0 or 1 is always 1/2 for each of these 4 states. Roughly, that's slightly simplified, but anyway, it's true that these measurements are chosen so that whatever Alice finds, she learns nothing about the initial state of A0. Now suppose the unknown state of A0 is alpha times 0 plus beta times 1. Then the initial state of the combined system is what I've written here, which might take a little while to parse. So A0 is the first of the 3 qubits. It's in the state 0 with amplitude alpha, that's these 2 bits, and in the state 1 with amplitude beta, these 2 bits. On the other hand, the last 2 qubits are in the state 0, 0 plus 1, 1. So alpha multiplies 0, 0 or 1, 1 for the last 2 qubits with the same coefficient. And likewise, beta multiplies 0, 0 or 1, 1. Now to see what happens after Alice makes her measurement, suppose she learns that the state A0, A1 is in this final state. After the measurement, B1 will be in this state. I wrote it should be an exercise, but to explain it very briefly, to find out the answer, you project onto the part of the wave function where the first 2 qubits are in the state 0, 0 or 1, 1. So that'll be this part or this part. But because of the minus sign, this one picks up a minus sign and this doesn't. So you get this state for qubit B1. Knowing that, so after Alice makes her measurement, Bob's state will be in this, Bob's qubit will be in this state. And then Alice can tell Bob that he can recreate the initial state by acting on it with this particular unitary matrix. So what the measurement outcome tells Alice is nothing about her qubit, but it does tell her what Bob has to do to recreate the initial qubit. The other cases are similar. So I wanted to explain a generalization which would have led us to the conditional entropy, but I think I'll have to leave you hanging and refer you to the written version if you want to hear more. I think that this is the basic case of quantum teleportation, and maybe my having described it briefly will be useful as a starting point for other lecturers. Thank you.